These are the main elements of a Comsol multiphysics simulation. And to illustrate this, let's take a look at a simple example. Consider the flow to a well at the center of an island. This is the island, circular. The well is right here at the middle. If we pump water out of this well, the pressure will drop. Because of symmetry, this is a one-dimensional problem. So we'll assume that the hydraulic heads, or the pressures, vary just along this line. This problem can be set up in Comsol, and I've done that here in this particular example. There are no global definitions used here, so we'll just expand the model that defines the problem. There are some local definitions. Expanding that, we see that first this is an analytic function shown right here. And this is the analytical solution to the flow to a well pumped at a constant rate in a confined aquifer. It's called the Theim solution. We also include these variables. These are constants, Q, the flow rate from the well, a variety of other constants, and some expressions like this one, the well flux. We define the name, what the expression is, the units, and we give some description here. These will all be available to use later on in the model. The geometry is shown here, and if we expand it, we see this entry called the interval. We click on that. We see that the interval consists of a left endpoint and a right endpoint defined at these locations. That plots up like this. This is the left endpoint at a radial distance of 0.1, shown right here close to this line of axial symmetry, and the right endpoint is out here. This is a one-dimensional problem, and we're solving it along this line. That's our geometry. There are no materials in this model. We're not using this, so we don't need to look at it. And I'll expand out Darcy's law. This is where we define the physics. Let's first look at fluid and matrix properties. Click on that, and you see here this is where we define the density of the fluid and the hydraulic conductivity of the aquifer. Those are the two parameters that need to be entered here. In this case, we've entered expressions, a variable called k and a variable called ρ1. These refer back to these variables that were defined up here. So ρ1 is 1,000 kilograms per meter cubed, and k is this value of hydraulic conductivity. These three entries are defaults, and we've selected, or we've entered in these two entities here, which are the boundary conditions. So if I click on that, this is a specified hydraulic head boundary condition. We can see that this boundary out here is selected. It's boundary number 2, and the hydraulic head there is 0. This other boundary condition is at boundary number 1. You can see that it's been selected. And this boundary condition is specifying the inward velocity equals to this term called well flux. And that's also defined up here in variables. In this case, we use a default mesh. The study is stationary. This is what Comsol uses for a steady state analysis. And if we press this equal sign here, then we run the model. And we get the results plotted down here. So I set up a plot that shows both the numerical results and the exact analytical solution. If we click here on numerical results, you can see that it's an expression called dl.h. That is the expression that's used for the hydraulic heads, and this DL stands for Darcy's Law, shown here, which is the physics that we selected for this particular model. So that's the numerical results. The exact results, they're calculated using this analytical function called Theim, and these parameters. And the exact result is plotted here as this green line, and the numerical results are shown here as the blue line. And you can see that they are quite similar here at radial distances greater than about 50 meters, and there's some differences as we get closer in towards the well at smaller radial distances. So we might be interested in the relative error between these two solutions. So if we click on this plot and expand it, we see that this plot consists of the numerical data described right there as that variable. This is the analytical expression, that's the exact value. So we take the difference and divide by the exact value, and that's the relative error. That's plotted here. You can see it bounces around at small radial distances, and then we have a fairly small error here as the radial distance increases. So we can plot both numerical results, analytical results, or we can write expressions and plot the results of those expressions.